Alright, so today we're going to be learning how to solve integrals using a technique known as trigonometric substitutions. And so this technique is like a form of the U substitution method, but we're going to be using trigonometric identities. And there's some caveats or like some special cases when we have to deal with trig substitutions. That's why it's covered separately. So whenever we see binomials in the form of a squared plus x squared or a squared minus x squared or x squared minus a squared, where a is a constant and x is the variable, that's where we can use trig substitution. So whenever we see this, just remind yourself to use trig substitutions. All right. So what is a trig substitution? So the most commonly used substitutions are us assigning x is equal to a sine theta, x is equal to a tangent theta, and x is equal to a secant theta. And this kind of represents like all the families of this corresponding to these binomials. And where am I getting all this from? Let me show you. So let's say like these like trigonometry is very related to the right triangle, right? So we're essentially substituting x for the variable theta, and that's the new variable we're defining. And that theta, when we integrate with respect to theta, hopefully we are able to find the integral of whatever we want to. So let's say we have a triangle, and then this is theta, which is the variable. If the opposite side is x and then the adjacent side is a, we know that the hypotenuse is simply equal to a squared plus x squared and the square root of that. And so if we make the substitution of x being equal to a tangent theta, and this just comes from our triangle of like opposite over adjacent is equal to tangent theta, so x over a is equal to tangent theta, and I'm just taking a to the other side. That tells me that the square root of a squared plus x squared is simply equal to the hypotenuse divided by the hypotenuse divided by the hypotenuse divided by the adjacent side, right? And we know that adjacent divided by hypotenuse defines cosine, and the reciprocal of cosine is simply equal to secant. And so a squared plus x squared and the square root of that divided by a is simply equal to secant theta. And if we were to take the a to the other side, we would get the square root of a squared plus x squared is equal to a secant theta. So notice how and this should be the absolute value of secant theta because we have the square root. And so notice how we now have a equality, or we now have a new substitution for a squared plus x squared, and that's just a squared secant squared theta with this substitution of x equals a times tangent theta. Similarly, for our other substitutions, let's draw our handy right triangle. We have theta like this. If this is x, this is a. Now, this length over here is simply a squared minus x squared. So this is the second case that I defined over here. Now our substitution is simply equal to x is equal to a times, well, opposite over adjacent, or opposite over the hypotenuse is sine. So this is just a sine theta. And therefore the square root of a squared minus x squared is simply the adjacent divided by the hypotenuse, which now will just become a times the absolute value of cosine theta. And so a squared minus x squared is just the square of this, and that will also remove the absolute value. To be more explicit, a squared minus x squared, we can just substitute it with a squared cosine squared theta. And so we have a special substitution over here. And then finally, for the case of x squared minus a squared, we have theta over here. And what length would describe x squared minus a squared? That would tell us that the hypotenuse would be of length x. And that would tell us that a would be on the adjacent side. And so we're trying to find this over here. And therefore, our substitution is x is equal to basically secant a times secant theta. And that allows us to get square root of x squared minus a squared is simply equal to opposite over adjacent times a. So that is equal to a times tangent theta, an absolute value. So notice how these three substitutions help us take care of these three cases of how the monomials can be represented. And we'll see how these substitutions will help us solve integral problems that we previously could not. And before we see concrete examples, one thing that we need to keep in mind about the trig substitutions is, let's just say we have x is equal to a tangent theta, and that's our substitution. This requires that theta is equal to tan inverse of x over a, and therefore the domain of theta, so that implies that theta is between pi over 2 and negative pi over 2. And the reason why like the domain restrictions, because of like the substitution, because like these domain restrictions come from the fact that our substitution requires this property of us being able to get theta from x, and this is known as like reversibility. And now that like we have restricted our domain of theta to a specific part, we know that like some other trigonometric functions can only be positive or negative within a domain. Like for example, cosine in this domain is always positive. And this is another fact that will help us down the line in solving integral problems once we have made the trig substitution. So with other substitutions, so if we did, this domain relates to when we've used x equals a tangent theta. If we did x is equal to a sine theta, then theta is equal to sine inverse of x divided by a. And now our domain is restricted to negative pi over 2 is less than or equal to theta is less than or equal to pi over 2. So we have the equality signs. And finally, when we have x is equal to a times secant theta, then we have theta is equal to secant inverse of x over a. And here, if you'll know that like the graph of secant inverse is disjoint. So if x over a is positive or is greater than if x over a is greater than or equal to 1, because secant inverse doesn't have a domain between 1 and negative 1, but if x over a is greater than or equal to 1, then theta, that implies that theta is between theta is less than pi over 2 and it is greater than or equal to 0. And if x over a is less than or equal to negative 1, then theta is less than or equal to pi, and it is less than pi over 2, or greater than pi over 2. So these are the reversibility properties, and they'll come in handy later. So I've given you all this information. Let's now work on some problems that use trigonometric substitution. So this problem says evaluate the square root of 4 plus x squared dx. And notice how we have this monomial, so that implies that we should probably be using trigonometric substitutions. So which trig sub will come in most handy? So 4 plus x squared will, the square root of that will probably imply that we'll have x over here, and we'll have 2 over here, and that will make this a squared plus x squared, and therefore tangent of theta times 2 is equal to x. So that's our substitution that we're going to make. And we need to relate dx to d theta because we need to switch up the variable of integration. So we get 2 times secant squared theta is equal times d theta is equal to dx. So that's our new dx, or that's what we're going to substitute in for dx. Now we have to decide on what to substitute in for 4 plus x squared. And we know that x is equal to 4 tangent theta, so what we get is this is simply equal to 4 plus, or x is equal to 2 tangent theta, so x squared is 2 tangent theta squared. And then this is dx. So we end up getting the square root of 4 times 1 plus tangent squared theta. And then substituting for dx, I get times 2 secant squared theta d theta. Now, using another trig identity, I know 1 plus tangent squared theta is simply equal to secant squared theta. So this is the square root of 4 times secant squared theta times 2 secant squared theta d theta. Simplifying this, I get this is simply 2 times secant theta, the absolute value, times 2 secant squared theta d theta. But because of the reversibility rules, I know that once I substituted in 2 tangent theta is equal to x, I'm restricting theta between pi over 2 and negative pi over 2. And in that range, secant theta is always positive. So I can remove this absolute value, and this is simplifying, and I can simplify this to 4 times secant cubed theta d theta. Now we just need to find out the integral of secant cubed theta with respect to theta. Right? And so the way that we will do that is we will approach this using integration by parts. So we'll treat u as equals secant theta. That means du is equal to secant theta tangent theta d theta. And dv is simply equal to secant squared theta. That means v, or secant squared theta d theta. That means v is equal to tangent theta. And then, therefore, we can use integration by parts to re-represent this as 4 times u times v, which is secant theta times tangent theta, minus v du, which is tangent theta squared times secant theta d theta. And now what's left is we need to integrate tangent squared theta times secant squared theta. And recall that tangent squared theta is the same as secant squared theta minus 1. So this integral, we can represent this as secant squared theta minus 1 times secant theta d theta. Now we end up with secant cubed theta, which is what we originally tried to find the integral of, minus the integral of secant theta d theta times d theta. So to summarize all of what we have so far, we have that the integral of secant cubed theta is equal to secant theta times tangent theta minus the integral of secant cubed theta d theta minus plus the integral of secant theta d theta. We can take this to the other side, right, because these are like terms, and therefore the integral of secant cube theta is equal to secant theta tangent theta divided by 2 plus the integral of secant theta d theta divided by 2. So now what we have left over is to find out the integral of secant theta d theta. And so let's work with that on another page. So yeah, this is a complex integral, and that's usually the case with trigonometric substitutions, but there's really not much else you can do. So a trick to find out this integral is we multiply our integrand by secant theta plus tangent theta. And this is valid because it's the same thing as multiplying by 1. Right? This fraction just evaluates to 1, but it will help give us a useful form. So once we do this multiplication, the numerator is simply secant squared theta plus secant theta times tangent theta divided by secant theta plus tangent theta times d theta. And now what we can do is now we can take a u substitution. If we do w is equal to secant theta plus tangent theta, then we get dw is equal to secant theta tangent theta plus secant squared theta times d theta. And so that just turns out to be our numerator. So we can rewrite this as dw divided by w. And that just turns out to be ln of absolute value of w. And then resubstituting back in the value of w, this is just the ln of secant theta plus tangent theta. So we found out the integral of secant theta times d theta. And so let's go back to our original integral. And finally, what we end up with is this integral of secant cube theta is just secant theta times tangent theta divided by 2 plus we got 1/2 ln of secant theta plus tangent theta. And then notice how in the original one we multiplied everything by 4. So all of these denominators of 2 just come to the numerator because we multiplied by 4. So that's what we have. And now the final step is we have everything in terms of theta, and now we have to convert back into everything we have to convert back into in terms of x. So in order to do that, we can use this like handy dandy triangle that we have. So this essentially becomes 2 times secant theta. So secant theta is simply hypotenuse over the hypotenuse over adjacent, and our hypotenuse is just the square root of 4 plus x squared divided by 2, and then tangent theta is simply x divided by 2, and then over here we have 2 times ln of secant theta, which is again the square root of 4 plus x squared divided by 2 plus the tangent theta, which is x over 2. And therefore what we end up with is what we end up once we simplify out everything is this. Let me split this up. This becomes these two cancel out, so we get x times the square root of 4 plus x squared divided by 2 plus we can do 2 ln, and then in this ln, if we take out 1/2 in common, you have 1/2 plus whatever over here. And then if we recall the rules of logarithms, you can split this into ln 1/2 plus the ln of the leftover, and ln 1/2 is just another constant, so we can yet again rewrite this as x times the square root of 4 plus x squared divided by 2 plus um 2 times ln of the absolute value of the square root of 4 plus x squared plus x, and then all plus c. And that is our integral. So this is one of the harder integrals, but trigonometric substitution is also one of more advanced concepts, and that's why it's usually taught at the end. But hopefully that made sense, and let's just do one more problem. So we want to solve for the integral of x cubed divided by the square root of 9 minus x squared dx. We see this monomial term, or this binomial term with this x squared, which implies that we should probably be using trig substitutions. So clearly our hypotenuse is 3 in this case. This is theta, and we'll make our since we only want to use sine, cosine, or sine, secant, and since we only want to use sine, secant, tangent, if we have the hypotenuse, the only ones that involve the hypotenuse would be we will probably be using sine in this case, because we want sine theta is the constant times whatever sine theta, so the constant will be in the denominator, and so the only one with the hypotenuse in the denominator is sine, and so this is x, and then therefore this is 9 minus x squared, and our substitution is x is equal to 3 sine theta. And with this substitution, we get dx is simply equal to 3 times cosine theta d theta. And this is all the information we need to re-express this problem. And so let's just re-express the integral. X cubed is simply equal to 27 sine cubed theta divided by the square root of 9 minus x squared. And 9 minus x squared is simply equal to 3 times cosine of theta, and because that's just the opposite times the hypotenuse, or opposite divided by hypotenuse, so 3 times cosine theta, and then now substituting for dx, we get 3 times cosine theta d theta is our dx. And since the domain is between, because of sine, our domain is between negative pi over 2 is less than or equal to theta is less than or equal to pi over 2. I think over here this should have been like absolute value of 3 cosine theta, because it could be negative depending on what our theta is, and this is square root. But in this domain, cosine theta is always positive, so we can just treat it as without the absolute values, and that just helps cancel these ones out. So we end up with 27 times sine cubed theta d theta. Let's remove the constant, so it's the integral of 27 sine cubed theta d theta. One way we can solve this integral is, we know that sine cubed theta is sine squared theta times theta, and 1 minus cosine squared theta is equal to sine squared theta, and this is from the trigonometric identities as well. So we can re-express this as 1 minus cosine squared theta times sine theta d theta. And the reason I did that is because now you can substitute in, you can use a u substitution, and if we change the variable, w is equal to cosine theta, then you get dw is equal to minus sine theta d theta. That helps us get rid of this term, and we end up with something like minus 27 times 1 minus w squared times dw. And now we can easily calculate this integral, which is just equal to, that integral is just equal to w minus w cubed over 3 times negative 27, right? And then now substituting in back for w, this is just the same thing as 27 times cosine cubed theta divided by 3 minus 27 times cosine theta. This is just 9 afterwards. So what we have over here is currently have 9 cosine cubed theta minus 27 cosine theta. And now we can finally substitute in back values for x. Cosine theta is adjacent divided by the hypotenuse. And so we know that this is just 9 times 9 minus x squared to the power of the square root of 9 minus x squared to the power of 3 divided by 27 minus 27 times the square root of 9 minus x squared divided by 3. So this becomes 9 minus x squared to the power of 3 over 2 divided by 3 minus 9 root 9 minus x squared plus c. Okay, this was very messy. Plus c. So that's our answer. And hopefully that was easy to follow along. Trig substitution can be pretty challenging, but it comes with practice. So hopefully this helps you get on a better direction.